We have Graeme Foster here today. He's going to talk about leveraging LLMs to build intelligent applications. LLM stand for large language model if people don't know what it means. So Graeme is a technical specialist in apps at Microsoft. He's been writing code for 40 years. I wasn't born yet, 40 years. Anyways, he actually my colleagues, and he said that I can say this, okay? He said that I can write Python better than him. And his demo today is not Python at all. I don't even know what language he used. Please welcome Graeme.
Cool, thank you, Gia. Everybody hear me okay? Yeah, awesome, brilliant. And thanks for sticking with us till this time as well. I know it's the last session of the day, so it's always a hard slog till here. So hopefully we can inject some really awesome LLM energy into this room this afternoon. So thanks to all the sponsors. Obviously, events like DDD, Perth don't happen without all of these amazing companies helping us out. So huge thank you to everybody up on that screen today. That's my last slide. I don't like slides. So I don't like Python either. So okay. See, I did that. I said that exact thing at a Microsoft event 3 weeks ago. And I swear nobody in the room cracked a giggle at that. So I feel like I'm winning already. So I will be spending my time today help. Oh, we're back. Awesome, cool. I'm going to spend my time in LinkPad. This is C# code, for those that aren't familiar with it. But don't worry too much, because it's not going to get that complicated. Actually, it looks pretty complicated, doesn't it? Mental note to self. I've seen a lot of pop stars fall off stages in the last few weeks. There's a huge drop about 2 meters back from me here. And I like to move around on a stage. So I'm kind of hoping I don't fall off, because Rob's got his video camera down there, and he might actually record that. All right, so when I first did this talk about a year ago, some people hadn't heard of things like GPT and LLMs and stuff like that. But I mean, let's get a show of hands in the room to start with. Who has actually used a large language model like GPT or Gemini or Claude? This might be the quickest talk of your life then. There's other talks on today. Who's used them in anger? Who's got kind of serious with them? All right, okay, cool. So, about a year ago when GPT first dropped, and everything I'm going to show you today is applicable to other large language models. It's not just the OpenAI ones, so everything here is kind of like across the board. But when GPT dropped, whenever it did, seems like a decade ago. I know it was only like a year ago. All of these frameworks started popping up around it. So you might have heard of things like LangChain, semantic kernel, there's Llama Index now, I'm getting a few nods in here. We have AutoGen, and everything looked magic, right? You kind of look at these things and you see the claims around them and you think, oh my God, like this, I don't understand it. And I don't know about you, but when I don't understand something, I kind of don't like that, because people are asking me about it. Like, what does this thing do? How does it work? And if I don't know it, my natural instinct sometimes, and I don't know if this is a good trait or not, is to go back to the very basics and to actually just play with the APIs, the raw API calls, and then see what I can do with them. And what was interesting about GPT was the more I started to play with the API calls, the more I started to get an insight into what tools like LangChain and semantic kernel and AutoGen are actually doing under the hood. And the more you do that, the magic and mystique of those tools starts to disappear. I'm not saying that large language models aren't kind of like magic under the hood. We all saw the keynote this morning, and there's some crazy stuff going in there. But when you start to actually build on top of them, there's actually not much magic going on. So that's what I want to do today, is really take you through my little learning journey of really dispelling all of that magic from large language models, but getting a really good handle on what they do and how you can bring them into your own applications. And hopefully that'll give you some ideas of how you could take this technology and implement it in a sane way, right? As opposed to something that they're not really suitable for. So that's the plan. And we're going to do it for a series of little C# demonstrations that try and explain what's going on behind the hood. So with that, I'm going to start at the first demo, right? So at the end of the day, all large language models are just a simple REST API call away from you. And they all work on the same premise in that you pass some text. We'll get into things like tokens and embeddings and stuff like that later. But you pass some text into them, and then you can pass a few little fiddle factors, like numbers that you can change to change the kind of output that the large language model is going to give you. And then the large language model will have a guess at probably the next most likely token, word, they're not quite the same, they're close enough, that might appear. And then it will push that back in. And given what you passed in and that new token, it will come up with another token, and then another token, and then another token, until finally it hits some kind of stop signal. That could be that you said, hey, I only want X amount of tokens, or it might just think, yeah, that's a good enough response. Everything you're going to see today is that. And it has some really kind of cool implications. So it starts off looking very simple, something like this. We talked about twiddle factors. Large language models have got a few key things that we can tweak. So we have a property called temperature. Raise the temperature really high and watch the output of a kind of open prompt. It's hilarious. The models get super excited. They're a bit like me after I've had a drink or two later on, if anyone is at the after-show party. And they come up with some crazy stuff. It's really good fun to watch. We've got this property called nucleus sampling factor. Basically, what did we say? It's an alternative to temperature. 0.1 means only the tokens comprising the top 10% probability will be output. Okay, we'll have a look at that in a minute. Max tokens. All large language models charge by tokens. You'll basically charge on the number of tokens you pass in and the number of tokens that you get out. So if you're smashing tens of thousands of these, you're going to get a really, really big bill if you've got a popular service. So think about keeping that down. Obviously, that's going to change the amount of output that you get. There's a few other things, frequency penalties, presence penalties. They all, again, just adjust that output. And then we have this thing called the deployment name. So in mine, I'm using GPT-4o. We all know there's a ton of models now, right? GPT-35, GPT-3, GPT-4, GPT-4 Vision. There's loads and loads and loads. So they're all trained in kind of to provide different capability outputs. At the end of the day, these models have pretty much consumed the entire content on the internet that's just being pushed into this huge neural network. And that's kind of what's going on, and very simplistic. Again, it was explained way better in the keynote earlier. But that's why large language models give kind of better responses on some things than they do to other things. Because really, the foundation models are all about what's the content out there on the training data. And they're really good at that. I saw one earlier about that maths test, where it's like 85% output on GPT-4o. Like, apparently, if you start to change some of the questions on that, then that really starts to drop quite significantly. So it makes you wonder about the training data sometimes. And then a really interesting one, log probabilities per token. So we then go to the actual prompts. And prompts really have got, let's say, 2 or 3 main components to them. The first is super important. It's called the system prompt. So this sets up the whole context for the operation or the interaction with the large language model. So you might have seen prompts where you say to a LLM things like, you are a pirate, you must respond like a pirate, or something kind of silly like that. And the point of the system prompt is that it's really kind of key to setting what that response is going to come out like. So without knowing the internals, it seems to have a much higher impact on the sort of output that you get. So you can see here, I'm going to tell my large language model, you're a poet. You create spellbinding, hilarious poems that are only 5 lines long in response to a prompt. So we've seeded that now. Everyone can see this at the back, can they, by the way? It's all good? Yep, perfect. And then we have the interactions. Now, we're using an API here called the Chat Completions API. Think of it as like modeling a conversation. We have the system prompt, and then we have the user saying something, that's me. And then we have the assistant, which is the large language model, will respond, and we can keep that conversation flowing. So in my case, I'm an engineer changing his demos on the fly in a live session. And then we can run that, and if all goes well, live demos. Dun, dun, dun. We get a huge amount of response back. Okay? So the important bit and this comes back as JSON. On the far right-hand side, let's see if we can scroll on this one, is my little poem that I get back in a live demo, nerves on high, switching code with a hopeful sigh. That's kind of fun, actually. But one of the important things about large language models is we talked about tokens and how what's going on under the scenes is that instead of coming up with a single big response, the LLM is outputting a response token by token and then considering the last output, putting a new token onto it. So with this little log probabilities per token option, we can get interesting insight into that. So you can see for the first word in my poem, we had in. But there were a couple of possibilities the LLM chose from, in and with. And then let's have a look. We had the word live come out. That could have been straight up to room. We had demo come out, demo session. So that's kind of what's going on, right? Everything you're going to see from now on is just a variation on this. Right? If I can give you one little piece of wisdom, follow the prompts. If you're not sure how an LLM works, set up a reverse proxy, have a look at the prompts. Some of them will alarm you, some of them will surprise you, some of them will give you joy and pleasure to read, because it's quite incredible to see how we get the best responses out of these amazing large language models. But let's say you're trying to write an application, because that's what we're here to talk about today. Now, those of you that have built applications for a long time will know that this kind of input, that little poem that we had, is not the easiest thing to digest inside a computer program if you want to do something more with that output. Like if all you're trying to do is show something to the end user, happy days. But if I'm building an application and I want to do something more, let's say I'm building a bank teller application. So I want to have a conversation with a human being, right? And I want to know what it is they want to do today. So I got rid of the prompt that I had earlier, which was probably a better one to have. Basically started saying, you're a bank teller. Let's go for this one. Tell me what the customer is trying to do. And we'll plug this one in, change on the fly, and then we'll have them say, what's my bank balance? That seems pretty good. See, I was changing my demos on the fly in a session. What have I done wrong? Oh, don't you love your string literals in C#? Damn it, why didn't we use Python for this? It would have been so much better. What's my bank balance? What's going to come out? All the way over here. The customer is trying to check their bank balance. Well, that's lovely, but how does a computer work on that? Now, what you'll find with large language models is that there's only a certain amount of input you can throw into them. So they all have these kind of prompt windows, maximum amounts of tokens that we can push through them. So to write an application, we start to have to think about, well, maybe, because we can't put everything in, large language models are a bit like people as well, even if you try and fill the token window, they're very good at remembering the top bit, and they're very good at remembering the end bit. But the stuff in the middle, which is probably like now for the next half an hour of my talk, will kind of disappear. And then you'll walk away at the end going, oh yeah, I remember the first 5 minutes. Python, .NET, something like that. What about the middle bit? So it's really impractical to just throw one prompt into an LLM and expect to get an output for your user. So we start to have to think about how can we actually tweak the large language model to give us things that we can actually use inside our control flow of our program. And this is how things like semantic kernel and LangChain are built together. They comprise of lots of small little prompts and interactions with other systems, and they chain everything together and then give you an output. So the first thing we're going to do is we're going to take that prompt we just saw, and we're going to add one little extra piece to it. So we're going to tell it, actually, I don't want you to give a lovely, fluffy response back to me. I want a single phrase. In my case, I'm going to say, choose from the following intents, like intent detection. Are they interested in account information, new accounts, new credit cards, branch information? Now, I've got this little bit down here, an example and a response. We call this like single-shot learning or multi-shot learning. The idea is that inside our prompt, we give an example to the LLM. Again, it's kind of like if you're a human doing a task and you're not quite sure how to do it, if someone sort of says, oh, and if this happens, then you do that, and you go, oh, yeah, right, I kind of get the gist of it now. LLMs are like that. So now, if we run this prompt with what's my bank balance, we're going to get back, if all goes well, a phrase, account information, which, and it doesn't always happen, you can be very careful when you're testing large language models, is very likely, is very highly probable to be one of these, unless it doesn't know what it is. And in that case, if I say something like, where are the fish? And I've never worked as a bank teller, but I would hope people don't come in and say things like, where are the fish? Well, it's a bit small, that, isn't it? But in the context now, it's no idea what we're trying to do. So I don't know. I have no idea. So this is cool, right? So we started to look at a little prompt here. But this is no good on its own. We've taken the conversation, and what we need to do now is say, well, okay, let's start thinking about what we do next in our IT system. So we're going to introduce a little chain into our prompt. See, that's my mouse kind of slipping down on the thing there. It's always hard doing mouses on lecterns. But what we're going to say is, look, let's try and work out what the intent of the customer is. And then if, I'm not going to show you the C# code behind this because it doesn't really add any value at all. But it's a little if-then check. And we're just going to say, look, if the response is unknown, then let's keep this dialogue going. Let's prompt the user for more information. So this is our second little prompt. And in this one, the prompt is very similar to the first. You're a bank teller, you're trying to find the intent of the customer. What would you ask the customer next to find their intent, given their current input? Respond with just the question. Okay, so it's pretty straightforward. So if we run this one now, and we're going to pass in what is my account balance, then the response that comes back is great, account balance. We can work with that. We'll get to that in a minute. But if we don't know what the user's trying to do, and you're going to see this little debug thing going all the way through, then instead of getting an intent back, we get a suggested response. So if you think of a chatbot situation now, we've got this little bit of code that can use the LLM to work out what the customer's trying to do. If we know what they're trying to do, awesome, we'll get to that. But if we don't, then we're going to come up with a suggested response. So pretty easy so far, and you can see this is pretty good. Are you looking for information about your existing account? Or are you interested in opening a new account or a credit card? Which is awesome, because this is all based off the intents that we have up there. Now, very simple one. So this is a long-running conversation. There's another key concept you're going to find in tools like LangChain and semantic kernel, and that's called memory. Memory is super straightforward. It's just this idea that we've probably got a stateless application, and we just need to retain this chat history somewhere. So we need to somehow store the conversation as it is. It tends to just get dumped in a database. There's nothing that complicated about it. There's only one thing I want to call out on here, and that's these conversations can get large over time. And because we have these finite-sized prompt windows, what you'll often see is that these tools like LangChain will have techniques to shrink the conversation history. So they kind of retain the essence of what's going on, but just kind of get rid of all the stuff that's not adding any value. So you can keep that token window for the really important things. So the bit here that's quite important, or probably more used to watch than the get intent of the memory, is the bit down the bottom. So you can see we've gone from this little dialogue, what do I want to do? Can you provide more specific information? Where can I catch a fish? And we've got the shrunk memory. The customer is seeking information on locations where they can go fishing. That's probably like a third the size or a quarter of the size of the conversation as it was. So memory, kind of, not really an LLM thing, but it's still really useful to know about. So we're going to move to the next key concept in large language models, which are called embeddings. So who's familiar with embeddings in here? Yeah, there's plenty of hands going up. There's quite a few not, though. All right. So I like to think of this in terms of a little example. Think of a word like cold. Right? So let's take the word cold, let's give it the number 1, okay? And let's think of the word hot. So we're going to take the word hot, and we're going to give that the number -1. Okay, so you see how I've kind of taken these two concepts, words at the moment, and we've turned them into two numbers, 1 and -1, which is great. Now, if you had something like freezing cold, like who could give me an idea of what number that might be? 2, we've got 2. Okay, so freezing cold is 2. What about boiling hot? again, it's going to be going the other way, right? -2. So what we're starting to do is we're starting to take words, language, concepts, semantics, and turn them into numbers that are related. Now, we could extrapolate on this, right? We could have a phrase like, I'm turning green, or a phrase like, I'm going green, right? Those are very similar words, but they have very different meanings. Turning green, going green. One is kind of saying, I'm going to be going green. I'm probably going to buy an EV. I'm going to, go off the grid, all that kind of stuff. But the other is, I'm turning green. Could be somebody at the party later on tonight, right? They're going to be really, really unrelated concepts. And if you look at the embeddings that get created, they're very different. Now, an embedding is more than one number. It's, depending on the model that you use, it can be like 1,500, something like that. But the basic idea is that we can take language and semantics and meaning, and we can feed that into a large language model, and we can turn it into a list of 1,500 numbers that capture the essence of what we've put into that prompt. And embeddings also have another pretty cool feature, which is that because they're coming out of the large language model and the LLM's been trained on all this data from the internet, there's a lot of different languages out there on the internet. It's not just English, right? So LLMs and embeddings are actually comparable across languages as well. So we have this kind of thing that can take text and meaning and semantics, and we can use images as well to calculate embeddings, which is also a pretty cool trick. And we can turn them into these long comparable lists of numbers. So it's, again, a pretty straightforward call to our LLM. We're just going to say get embeddings, and this is just the kind of output that you get, a huge list of numbers. But these have a little trick up their sleeve. Because vectors, it turns out, are comparable things. So if we put all of these in a database, so let's say we've got a book, and we've got a whole bunch of vectors out of it. We put them in a database, and then the user comes along and they enter some text. We can now go to the database and say, look, we've got this bit of text here. Do you have anything that's similar to it? So in maths, they call it a cosine similarity search. And it's a super quick operation for finding text that looks similar, related to what we're trying to search over. So let's move on to number 6, I think we're up to. So this is the essence of a pattern called RAG. So anyone in here has heard of that? It stands for Retrieval Augmented Generation. And the idea is that because we can't put, again, the entire works of Shakespeare, let's say, into a single prompt, if we need to somehow search over that, or let's say it's our own corporate data, right? We need to search over our own corporate data. That's not in the foundation models. They know nothing about my procedures. They know nothing about my data. So if I can find a way to take my data and store it in a database, and then allow this kind of natural language similarity search over it, then I'm going to hopefully find something that's really relevant to help my customers. So think about searching unstructured data, corporate policy documents, that kind of thing. So the way we do it is we take these big documents and we start to snip them into what we call chunks. So when you want to talk to your data scientists, there's a real art in chunking documents. Simple techniques might just take like 100 words. You might find more complex techniques that can look at the documents and pull out metadata about images and graphs and things like that. And the whole point of this is it's like a pre-processing to be able to index our content in such a way that we can search over it later. So again, there's tons of ways you can approach it. Like, not all chunking strategies are the same. But the whole intent is to be able to get our embeddings in the database. And I've got a couple of documents that I've indexed, actually 2 very simple ones. Let's have a look ahead. And then I've done the text from Alice in Wonderland, like the story. So the first one, I had a very simple PDF file, and it just had some fictitious opening hours of a store. And we can search. We're just going to use Azure AI Search here, but again, you can use any database that's got vector indexes. So Postgres has got them now. I think most vendor-provided databases have got support for vectors. So it's pretty much a commodity thing. And we can see on my first search, what are the opening hours of our store on Monday? I get this huge chunk of information that's come back. And if you have a quick read of that, you'll notice that there is information about opening hours of stores. So all good. That's my first one that's worked. Let's go for what are the colors of the rainbow. And the document that this one fetches back is a very simple PDF file. Chunk 0 of the PDF file. The colors of the rainbow are red, orange, yellow, blah, 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 blah. I'll spare you all my French. I'm from Northern England. It's not a pleasant thing to listen to. But if we can throw a query in French, and I've tried this in Klingon as well, turns out there's actually half-decent support for Klingon out there on the internet. Who'd have thought it, right? So it comes out with pretty good results. But here you can go, like the colors of the rainbow are red, orange, yellow. One thing I've learned since I first did this talk, actually, Azure AI Search has got the concept of, they call it hybrid searching internally. So what that means is that it will not only search over embeddings, but it will search over text as well. And then internally, it will run a re-ranking algorithm and give you the best results based off embeddings and text. So if I was doing this demo now, and this is what I've seen most tools do today, is they actually ask the LLM to translate the text before they call the search engine. And then they pass the text in the language of the document. So then you get the best of both worlds. But if you've just got embeddings, then this is absolutely fine to do. Again, a couple more little examples. Let's go for where did the white rabbit live? So again, this has taken the whole Alice in Wonderland, and we've embedded that. And in this case, again, a lot of information in there, and it's found chunk 9 of Alice in Wonderland was the best chunk for that. But there's a ton of information in here, right? So this is not something that you could go and put back in the hands of the customer straight away, because even though the information might be in there, it's not exactly easy for them to find it. So the question is, what do we do? And it just so happens we have this very powerful natural language engine at our control. So what we do is we create another prompt. So again, this is why LangChain was called LangChain, is because it's all about chaining these little prompts together. And in this one, and we follow it down here, so we know the intent, and then if we detect, I think in this case that it's branch information, then we're going to do the search, and then we're going to call present results. And the prompt in this case, straightforward. This time we're seeding the LLM saying you're a summarizer. You need to extract the relevant information from the excerpt that you're given, and then look at the customer's question and answer it based off that content. And say unknown if you don't know how to answer it. That's quite important in LLMs as well. A really good tip one of my colleagues told me is that if you don't tell an LLM to respond with unknown if it doesn't know the answer, then it's very likely to hallucinate the answer, which is not a scenario you want to get into. So always put a stop criteria. And this bit here is super important. You must respond in the language the user asked the question in. I moved from 3.5 to 4.0, and the way that I phrased this, for some reason, always gave an answer in Spanish. I have no idea why. I asked it to tell me why, and it told me, when I said, tell me why you're giving the language you're giving the answer in, it then went back to English. It was like a Heisenberg bug in the system, so it was so difficult. I asked it, tell me why in the language you're answering the question in, to tell me why you're answering in that language. And eventually we got there, and it was just the phrasing inside the LLM. So testing is so important. Like, if you can't just up the model in production from, say, 4 to 4.0, because that could have huge ramifications on the answers that come out. So always make sure you've got a really good kind of LLM ops pipeline in there to make sure that things are going to work if you up those models. Now, in my case, though, let's run this one. So we go, what time is my branch open on Friday? So we're going to detect the intent. We go and run the embeddings. We know it's a search. We search against the vector index. We pull up the answer. And now, from the document chunk, we get the suggested response. Your branch opens at, 8 a.m. on a Friday, which, if we look in there, hopefully that's good. Friday, 8 a.m. to 1700. Now, again, there's a few more interesting prompts here. Where's my mouse gone? There it is. Awesome. So let's start with an obvious one in French. What time does the shop open on Friday? 8 a.m. le vendredi. So that's right, which is good. I know that one's right. The implications of this are huge, right? Because so many organizations have got people whose primary language is in English. So given the ability to take all of your content that's in English, create the embeddings, have a natural language search over it in the user's preferred language, and then even give a response in the preferred language is amazing, really. It's a very, very powerful tool that we've got here. And finally, in this one, and I'm going to take this one just for a bit of live, again, fun. And let's just pull up Google Translate. Google Translate. And let's see. Enter text, auto detect. I think. So Japanese to English. Mondays, the store opens at 9 a.m. I don't want to put the question in case the question says, like, when does the store open on Friday? Because that would be a little bit embarrassing, but I'm sure it wouldn't. And similarly, if we go back to the White Rabbit one, so let's go for the one before. If anyone here does speak Japanese and can confirm that that did ask on Monday, though, that would be pretty good. Where did the White Rabbit live? This one was more complicated because we pulled out a big chunk of information. We do the search, and we're told the White Rabbit lived in a neat little house with a bright glass plate on the door engraved with the name White Rabbit, which is awesome. I'm going to call this base rag. So Michelle Sanford, who's talking at the moment, and I did a talk a few days ago on a newer technique called graph rag. So one of the drawbacks you'll find with this method of doing rag, where you're basically running over the text and taking it chunk by chunk, is that to get a good response to the user, you need their answer to be in a single chunk of information. So that works really well for kind of pointed questions like I've done here. Where did the rabbit live? What time did the shops open on Monday? But if you start asking meta questions like, what are the key themes in this document? Then this kind of rag is not going to cut it. Because at best, it's going to pull back 2 or 3 chunks of information from the entire document. And you can't get all the themes of the document from that. So techniques like GraphRag, which we won't go into today, they're really worth looking into because they build this huge knowledge graph up front. It's like a graph database with nodes and edges. And then they use different techniques to try and find the answers to your queries, still using the LLMs, but by walking over these graphs and finding information that could be scattered all throughout the documents. But in our case, this is cool. So this is RAG. This is kind of searching over unstructured data. And all right, that's great. And it was one of the first early use cases of LLMs. But most organizations have been building APIs for the last 20 years or so, right? So we've all heard about the API economy. So many orgs have built thousands of APIs that unlock the company's information. So what would be really cool is to be able to integrate with those and create these natural language experiences so that we can have a chat, but in the background, be finding the information the user needs by calling our APIs. So that's the next thing that we're going to look at. This one is called function calling. So the idea behind function calling is that what we can do is we can take a whole bunch of APIs and we can create JSON schema definitions of those. So I've got a very simple one down here. It's just called get account information. So this is an API that exists in my organization today, and pretty straightforward. I've got a description. It gets bank account information, given an account number, and then there's different types of information that we can get about the account. What we can do is we can advertise these to the large language model and then ask it the customer's question. And if the large language model thinks that one of my APIs is going to be useful to help to get to the information, then it will tell me that. And then I can go and call that API and present the data back into the large language model to help answer the user's query. So we can pass in like a lot of different functions. They're more generic now. When I first did this was a new thing. It's called function calling. We refer to them as tools now. And tools can be other things as well as functions. So you might have seen examples where you have things like code interpreters. So you can get a large language model to create Python code. They're really good with Python code. The C# code, not always as good, so probably should have been in Python for those demos. But then we can take that Python code and we can throw it into an interpreter, get the result, and then pass that back into the LLM or straight back to the user if required. But the general gist of it is that we basically tell the large language model, here's a function, and then we're going to say, what's the balance on my account? Now, this one's quite interesting. On this one, what you'll see, and again, this was a change from 3.5 Turbo to 4.0 that threw me, first of all. With 3.5 Turbo, this would say, call the function, but I don't know what the parameters are. Whereas with 4.0, there's clearly some more training that's gone into it in the back end now, and it never comes back with the function call if it doesn't have the parameters, or if it knows you can't call it. So instead, it comes back with something that could be useful to ask the user. Could you please provide your account number so that I can retrieve the balance information for you? Now, if we've got all of the information that we need in there, what's the balance on account 1, 2, 3, 4, 5, 6, 7, 8, 9? Then what we get told by the LLM is, hey, go and call this function. And we can pass a whole bunch of functions into it. And what you'll find is that as you start feeding the results from the functions back in, then that might cause it to say, call this function, call that function. Or it might finally hit a point where it thinks it can answer the question. So what we end up with, and we'll bring it all together, is this big chain. It's comprised of about probably 3 or 4 different calls to LLMs, some embeddings, maybe some AI search, maybe some API calling, to allow us to detect the intent from our users. So in this case, what time is my branch open at? We're going to go down here. We're going to do RAG search. We're going to fetch embeddings, vector index, blah, 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 user sentiment, branch information, and finally we get down there. All the way through to calls like, what are the last few payments on my account? So this one's going to take a different path. It's going to detect that it can make use of account information and the API calls. And we can go and call the API, get the data, and similarly to with the search result, we can feed that back through the LLM. So there's another little prompt down here which says, present the API results. Again, just a prompt. You're a bank teller. You receive the following data in response to a user's ask. Format the data in a concise way to answer the user's query. You must respond in the language the user asks in. Okay, so we've now got searching over unstructured data. We've got the concept of long-running chat histories, so we can interact with our users. We can tap into all of our APIs. So this is looking pretty cool. But there's probably one big problem with all of this. And that's that the amount of code I've now got to do this is really getting quite large. So there's, I think, the helpers have been under, I normally hide the regions, but here we go. There's the helpers up here. We've got prompts. We're calling OpenAI, we've got more prompts, we've got all these tiny little building blocks of code that we need to make this stuff work and hang together. And if you had to do this for every single type of interaction you want to have with your users, that's going to become a nightmare, right? So this is just to get a little bit of information, but let's say we've got 500 business processes that we want to expose to our users. We don't want to have to codify every one of those to be able to make that work. So we're going to have a look, running low on time, aren't we, actually? That's gone so quickly, into a really cool concept, which are called plans. So these first appeared in semantic kernel, but they're now in most of the LLM frameworks that you're going to use. And the general idea behind them is that what I've shown you is essentially a bunch of small little building blocks. So I've got API calls, I've got unstructured searches, I've got the ability to summarize things. So if I could take all of these little building blocks, and then I could say to the LLM, look, the user's trying to achieve this goal. I don't know how to do it, but I've got a bunch of things that I think can help us get there. Can you structure these for me in such a way that we can get the output for the user? Now, the first time I saw this prompt was in semantic kernel, and it is a crazy prompt. In semantic kernel, it's got all sorts of things about rewarding the LLM if it does well. LLMs do really better if you reward them. Like, I will give you $1,000 for every good result that you give me. Worse still, if you threaten an LLM, it will work really hard to give you a result. Probably like humans, it might not be the best result, but it's going to work really hard. But these are all the kind of little things you see come out if you follow the prompts. This one's a bit simpler. What I'm going to do is I'm going to ask it to output some JSON for me that will describe how to achieve the goal. I'm going to give it the user's goal, and I'm going to give it some skills that it has access to. So in my case, and LLMs are really good at understanding text. The more metadata you have, the better this is going to work. If you just give it the names of functions, it's far less likely to give you a good output. But this one, I can summarize content. I can search for branch information. These are all little skills that I have. I can get embeddings for text. I'm describing inputs and outputs. And then what I do at the end is with one-shot learning, I give it what that might look like. So I'm telling it, I need your output to look like this, basically. And then what we're going to do is we're going to set it to task. So let's go and give it a goal for the user. The user wants to know what time their branch will open at on Sunday. Now, this is pretty cool. None of the other stuff wasn't. This is actually really cool. So here we go. It thinks to do this, it's going to go and extract key terms from the function. I've asked it to tell me why. Extract key terms from the user's question about branch opening times. Here's the inputs and here's the outputs. So we can start to now, using code, chain all of this stuff together on the fly if we want to. It's then going to decide to call the embeddings function. Generate embeddings with the extracted key terms, perform a search. Once it's done that, it's going to go and call the search branch information using generated embeddings. It's then going to get the result from that, and it's going to call the summarize content function. So this is so cool, right? I have not had to codify this process. I've just given the LLM the little building blocks and the goal of what the customer is trying to achieve, and it's worked to come up with these. Now, I'm not saying you should do this in production in real time, but this could be really good as kind of how do I create all of these little workflows? Well, I'll run them ahead of time. I'll come up with a bunch of goals that I think my users will have, and I'll get the LLM ahead of time to come up with the plans, because these are quite expensive. So that's like the recommendation if you're using something like semantic kernel, is to do it in that way. I've got another one here. I haven't run this one for like 6 months. I've no idea if this one's going to work or not. So I mean that. I have no idea. So what are we doing here? Get account details. Straight away, it's gone to call that. We asked for the balance on account 123. It's told me the input and the output. It hasn't summarized the output. We didn't ask it in the goal. Like, you must present the outputs nicely to the end user. That probably would have got the summarize call in. But this is the kind of thing that brings all of these building blocks together in a really powerful way, is the concept of plans. Now, there's one, how long do we have? I got 1 minute, is it? 1 minute. Agents. Everyone's talking about agents today. Agents sound super complicated. They're actually not. All an agent is think of like, if you're trying to achieve a complex task, you probably can't do it on your own. You're going to need a bunch of helpers, and those helpers will be specialized in different things. So agents are really just different large language model system prompts that retain their own threads, and maybe external tools that can help. An agent doesn't have to be an LLM. But the idea is that an agent framework will bring all of these together. It will basically ask a coordinator agent and say, we're trying to do this, what should we do? And the coordinator will say, you should go and speak to that agent that can, let's say, go and extract information from a database. You get the information, hey, coordinator, we have this. I think you should speak to that agent. And with that coordination, we can solve really complex tasks, or we can solve really silly tasks. I've got a 2-agent system here that are playing a game of guess my number. Again, agents all work like this behind the scenes if you follow the prompts. You tell the agent what its job is. In my case, you've got the number 53. Agent 2 is going to try and guess it. And then if it guesses too high, say too high. Too low, say too low. And the format of your output must be who you are, who's the next agent to call, and what it is we're going to pass them. And then we have the second silly agent. The second silly agent is trying to guess agent 1's number. So we just tell it, like, a number's going to come in. You're going to try and guess a number. You will be told too high or too low. And then once you've come up with your guess at what it is, then we're going to pass that back to the other agent. So pretty straightforward. There are different ways you can set up agents, but the kind of ethos is this. They're both going to have their own separate conversation history, and then we can set them off. And when we run this one, here they go. Obviously, you will use agents for far more complicated things and trivial tasks like this, but this is the essence of all agent frameworks. Love it. And that's why you don't follow my prompts. So I got all the way through those demos until the very last one failed. Is it 52? It actually is 53 if I recall correctly, but that's okay. We almost got there. So look, that's the last demo that I've got for you. If I could give you one piece of advice with LLMs, it would be there is no magic outside those foundation models. Stick a reverse proxy, follow the prompts. Most of them are open source anyway, so you can go and see them. And they are super inventive. They will give you your own ideas on how to structure all of this stuff. And with that, go have fun with LLMs. Thank you, everybody. Cheers.